All right, so we're going to go ahead and get started on this next section. And this section is called Related Rates. And in this section, what we're looking at is exactly what the title says. We're looking at rates of things that are changing that are related to one another. So the example that I feel like is a really good kind of tangible example that we all understand is if you are at, let's say, a family gathering of some sort and you've got a pitcher of what looks like tea here, and you have these, most of us have seen a sort of pitcher where you have this little tab that you flip up here, and then the tea or whatever's in it comes pouring out. And at the beginning of the party, this pitcher is full and the tea comes out really quickly. So you've got to be careful and not leave that tab open too long, and as soon as your cup's full, you close it. Well, as the party progresses and the level of tea in the pitcher goes down, when you open that tab, it comes out like a dribble, and you're tilting the container forward to try and get the last drops out. And so we can see that the rate the tea is coming out changes depending on how full the volume is. So there's a number of things changing in this picture. The volume of tea in the pitcher and the rate the tea is coming out. So this is the type of problem that we're going to be looking at. And when we're looking at these types of problems, I've written out some steps here that are helpful. Always, it's really nice to draw a picture and just be able to visualize what you're talking about. And then we want to identify what rates we're given and what rate we are looking for. We'll write some equations and how these variables are related to one another. We'll differentiate the equation that we're looking to find the rates for. We're going to substitute in what we know, and we're going to look over our answer. You always want to make sure that it makes sense with what the question's given. For example, if you're looking for a distance or the rate a distance is changing, you're probably not looking for a negative number because distance can't be negative. The rate can be, but the distance itself can't be. So again, you want to kind of keep those things in mind and keep the context of the problem in mind. And then I've also written some other suggestions here. Ultimately, when we have quantities that we're plugging in, we want to plug those in after differentiating. If there's a quantity that's getting smaller or a rate that's getting smaller, then that should be a negative number. And when we're typing our answers into WebAssign, it usually takes positive answers. So the derivative of position is going to be distance or length. Talking about the position of the moving object, referring to its distance or its length, is velocity. And then we want to keep track of what variable we're differentiating with respect to. Oftentimes, the variable we're differentiating with respect to is time, but not always. So let's look at kind of a basic example before we get into the real types of problems we're going to be looking at. We've looked at an equation almost identical to this when we were doing implicit differentiation. So if I'm asking you to find dA dB, this is telling me what's a variable, what's a function, and what's a constant. So typically we see dy dx. So that means that A is a function, B is our variable, and that means C is going to be acting like a constant. So when we differentiate here, we will have 2A dA dB. And when we learned implicit differentiation, one of the things I mentioned is that we would just use A prime to make our notation simpler, but that sometimes we do want to use this notation. This section, you want to use this notation all the time. The reason why is we're going to have multiple variables, and we always want to know what variable we're differentiating with respect to and what's our function. And so it's really important that you're using this notation as opposed to just writing A prime. Because when you write A prime, you don't know, is it B or is it C that you're differentiating with respect to? So make sure that you use this notation throughout problems with related rates. And then we have the derivative of b squared, which is just 2b, equal to 0. Derivative of a constant is 0, derivative of a constant is 0. And the reason we don't have b essentially here is because b is our variable. A is a function, so that's using implicit differentiation here. So solving for dA dB, we can subtract 2b, divide by 2a, dA dB is equal to negative b over a. So we're going to be doing problems similar to this. They'll definitely be a little bit more involved than what we did in this example, but this is a good kind of getting our feet wet type of example. This next example is also a good kind of just exploring this idea kind of example. In this problem, we have a rectangle that's changing in size. So it's changing as time is passing. So when no time has passed, the rectangle is starting out with a width of 10 and a length of 7. And what we're saying here is that the width is going to be increasing by 5 each second, and the length is going to be increasing by 3. So my length is going to go from being 10 to being 15, and then 20, and so on. And the length is going to go from being 7 to 10 to 13, and so on. Well, we can find the perimeter in the area for each of these respective rectangles. So go ahead and pause the video here and fill out the rest of this table. And then I'll resume in just a moment filling in the table. So hopefully you did pause the video, and let's go ahead and fill in the rest of this. We've got 25 and 30, and then 16 and 19. And then the perimeter for this rectangle would be 34. The perimeter for this one would be 50. The perimeter here would be 66 and 82 and 98. And then the area for this rectangle would be 70, 150, 260, 400, and 570. So we not only want to look at what's changing here, but we want to look at the rate at which it's changing. So if I'm referring to the rate that the width is changing with respect to t, that would be dw dt. Now, we can see that the width is changing at a constant rate. It's increasing by 5 each time. So that rate is 5. We don't have units, but we'll just say 5 units. So it's increasing by 5. If it was decreasing by 5, we would say -5. Similarly, dl dt, the rate at which the length is changing with respect to time, is 3. It's increasing by 3 each second. The perimeter, let's see if it's increasing at a constant rate. From 34 to 50, we're increasing by 16, and then by 16 again, by 16 again, by 16 again. So the rate at which my perimeter is increasing is also constant. We can call that dp dt, and that's 16. Is the same thing happening with my area? From 70 to 150, that's increasing by 80. From 150 to 260, that's increasing by 110. From 260 to 400, that's increasing by 140. From 400 to 570, that's increasing by 170. So it's clearly not increasing at a constant rate. So dA dt is not a constant. It's an equation. So we can find an equation for that, but that's not necessarily what we're going to be doing with these problems. What we would be given then is, if we have these rates, we're going to want to find what is the changing area at a specific moment in time. So at 3 seconds, or when the width is 25, or when the perimeter is 82. And so they're going to give us some sort of condition as to when we want this rate. So let's look at the next example. Again, still kind of an introductory type of example. It says, at what rate is the area of the rectangle changing if the height is increasing at 5 units per second? So this is the rate the height is changing, so dh dt, and it's with respect to time. So that would be increasing by 5, so +5 here. And let's go ahead and, while we're at it, draw a rectangle just to have a visual, have a picture here. Our height and our length. And it says the length is decreasing by 3 units per second. So dl dt is -3. It's decreasing by 3. And then it says when the height is 4 units and the length is 10, we want to find the rate the area of the rectangle is changing. So dA dt, that's what we want to find. So you can see that as we read this problem, we're taking notes on what it's telling us. We're making notes about what it gave us and the conditions that we have here, and then what we're looking for, and we drew a picture. This is something that you want to do each time. This will help keep you on the right track as you're trying to kind of figure out what this problem is asking you to find. So the only thing we're missing here is how height and length are related to area. So area is equal to height times length using the terms that we're using for this problem. And this is the function that we want to differentiate. So when I differentiate, I have dA dt. And because both of these things are changing, the height is changing and the length is changing, they're both functions of things that are changing. So we do actually have to differentiate both of these using implicit differentiation. Now, because both of these are changing, these both represent functions, and a function times a function requires the product rule. So what we need to do here is use the product rule. So we're differentiating the first function. The derivative of h is dh dt. So we have L times dh dt plus height times dl dt. And now we have a function that we can work with here. And my work is kind of starting to get muddled together here, so I'm going to try and organize it a little bit better here. But if we're just working with this equation here now, I'm trying to find this. And I know at what length I want to find this at. I know my rate, the height is changing. I know at what height I want to find this. And I know the rate, the length is changing. So I can plug those in. Our length is 10. dH dt is 5. Plus our height is 4. And dl dt is negative 3. So 50 minus 12 gives us 38. And we're talking about, let's see, what units? We're just saying units per second. So units squared per second for area. All right, so that is a pretty, in my opinion, easy example, introductory example of related rates. We're going to do one more example in this video, and then we will stop this video and continue on with some more challenging examples in the next video. So this example says air is being pumped into a spherical balloon so that its volume increases at a rate of 100 centimeters cubed per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? So let's start out with a picture. We've got our sphere, and imagine this is three-dimensional, not just a flat circle, but we've got our spherical balloon here, and it's being pumped up, so it's getting larger. So I'm going to draw these little arrows just to remind myself that this balloon is getting bigger. And then we also have the diameter of the balloon. Now we know that the volume of a sphere is 4/3 pi r cubed. Okay, so this is kind of an idea of what's going on here. Part B says, what values do we know? What formulas involve the variables that we need? So let's look at the question again. Air is being pumped into a spherical balloon so that its volume increases at a rate of 100 centimeters cubed per second. So dV dt equals 100. It's increasing at a rate of 100 centimeters cubed per second. We just wrote this formula down here, but I'll write it again. The volume of a sphere is 4/3 pi r cubed. And we want this when the diameter is 50 centimeters. Well, what would the radius be here? If the diameter is 50, the radius is 25. The reason why I'm wanting the radius is because that's what I have in my formula here. So what we're looking for is how fast is the radius of the balloon increasing. So that would be dr dt when the diameter is 50 centimeters. So this is what we're looking for. So part C says, take the derivative of the formula involving r. Make sure you know what you're taking the derivative with respect to, and then we want to solve for dr dt. So this is the formula we're trying to differentiate. There's only one variable this time, so there's no product rule or anything like that. So we have v equals 4/3 pi r cubed. When I differentiate, I have dv dt is equal to, bringing that 3 out front, it will reduce with the 3 in the denominator, so I just have 4 pi r squared dr dt. Because inside this, essentially we have the chain rule. The outside function is this cubed, but r is changing. And so that represents a function. The derivative of that inside function is dr dt. If we solve for dr dt, we have dv dt times 1 over 4 pi r squared. So we can go ahead and solve for dr dt by plugging in the things we know. Dr dt is equal to, dv dt we know is 100 times 1 over 4 pi, and the radius we're looking at is when the radius is 25. So when I simplify all of this, we should end up with 1 over 25 pi centimeters per second. And that is our dr dt. And I think this is a good place for us to stop this first video. In the next video, we're going to dive into some definitely more challenging examples.